All right. Thanks, Yuanhan, for the nice introduction. And can everybody hear me well?
Yes.
All right. I guess I can just get started. So, hello, guys. Today I'm going to talk a little bit about our recent research in the intersection between two prominent concepts. So, one is something we call open work. I guess this is a really common term in the computer games domain, but we will argue that this is also a recent trend in machine learning and AI research in general. And the second concept is called embodied AI, which is kind of like the ultimate goal of AI, where we like to build up some agents that can actually perform some actual actions in the physical world and collaborate with us. So let's get started. So I guess there's no doubt that machine learning is stepping into a new era today. And one of the indicators is that today's model compared to maybe a few decades ago is much larger in terms of the number of parameters and energy and computation it's gonna cost. And such indicators not just means a lot of things. And one of them is that current machine learning model is definitely more capable than a few decades ago on completing a variety of tasks. I mean, these more variety of tasks or more powerful in terms of task accomplishment could be a little bit vague. So let's just focus on a single angle of that, which is the kind of like the concept or the category the machine learning model is able to deal with. It's clear that maybe two decades or even 3 decades ago, our model is still struggling on recognizing digits, which is actually just a very limited number of classes, like 10. But maybe starting at 10 years ago, like starting around like 2012 or something, our model is started to able to master tens of thousands of classes like image recognition. This is quite impressive, but not even comparable to what our model can do today. Today's model from OpenAI like DALL-E is able to not only recognize, but also create images with concept that doesn't really even exist in some of the existing data sets. For example, like this astronaut riding a horse, I'm not sure this such concept will ever exist in previous data sets like ImageNet or web or even web scale collection. So that really means that with such massive amount of computation and number of parameters, our model is really being powered with some amazing capabilities on recognizing concepts or semantics. And that really suggests that machine learning today, at least from this direction, is stepping from a more closed world or closed vocabulary setting to open world setting, which is actually much closer to our real world and our physical life around us. So, and that really means that another thing that to step into the next goal of AI, which is building an actual agent in the real world, we have to embrace this new trend to make sure that our embodied agent can also do the same thing. And I'm so glad that many folks in the embodied AI community has already, kind of realized such thing is happening. So let's just take this data set as an example. GetNet, which is a really famous data set in embodied AI or 3D understanding in general. When it started like a few years ago, I mean probably like 7 years or 6 years ago, it's a really small data set that only contains like 20 classes, which is very easy to recognize, or at least it was deliberately simplified to kind of to be more compliant with the models back then. But today, with today's powerful model, like vision language model, large language model, it is able to recognize a more wide range of tasks. For example, in this GetNet has been recently upgraded to 200 class, which cover many more categories that previously model cannot even imagine of. And we can even make this idea even crazier. For example, in this recent research of OpenSea understanding, the model is able to recognize even more open vocabulary of a concept. For example, like whether this object is made of metal or whether there's an area we can sit. These are clearly not the canonical category we would have imagined maybe a few years back, but it's definitely become more and more doable and more possible with today's powerful models. And this is only just one end of the story in embodied AI on the perception side. How about embodied actions? So let's just take this, very famous navigation problem as for example. Maybe when the embodied AI or such environment or the set of tasks like navigation manipulation was first introduced, like a few years back, the only thing we can imagine is to navigate to tables, chairs, baths, toilets, some very common and simple category. But how about finding some object that you as a user might not even be aware of? For example, like find a gingerbread house. This is a really complicated concept, but with the help of this large model, this agent can not only recognize this concept, but also navigate and perform actual actions to accomplish this goal of finding this object. So what I'm calling here is really about a paradigm shift for embodied AI. So maybe it started like a few decades ago, and even for today, many of the embodied AI researchers are still working on some contrived in settings where the tasks are very limited and designed by humans, look very artificial, and the environment we're dealing with are kind of static, and the whole setting is just kind of closed work. But what I'm talking about right now is that with the help of these recent large models, including large language model, vision language models, and many more, we should be able to migrate to a more realistic setting where there are going to be a massive amount of tasks for the agent to accomplish. And the work has to be dynamic and open-ended. So that really motivates today's talk. We are kind of rooted in the core concept of embodied AI, but we would love to add two new layers of complexity to embodied AI. So one is generalist. So how can we make sure that our embodied agents can be more general in terms of generalize to a new environment and accomplish more tasks? And also, we would like to make sure that our embodied agent can perform pretty well in an open world, which is compared to the previously had been pretty chattered closed world. And the open world concept is definitely more relevant to our human life, and to also make the robot coming out from this research more deployable to our physical world, or maybe in our house. Okay, so with that in mind, I would like to proudly introduce you with some of our recent work coming out of the team. The first work is something called Leo, which is an embodied generalist agent we recently built on top of some, really amazing kind of large language model and large vision language model today. And we also leverage many of their concepts to build this model. And this model is able to perform a variety of tasks in the physical world, the real world. And also, we would like to step back a little bit into the digital world again, and to introduce you to Craft Jarus, which is a series of work where we are trying to build a generalist agent in the Minecraft universe, and to see and really push forward the boundary of what this agent is capable of doing with the help of the large models. And there's definitely more work coming out next, but in today's talk, I'm going to just focus on these two. So let's just first start with Leo. So Leo is really about a embodied generalist agent that built on top of some of our recent research on, including 3D language learning, like the model, the data set, and some of the recent work. And the Leo paper itself is, I would call it a preprint, because it has been on hold by archive volunteer for more than 2 weeks for some unknown reason, and there's nothing I can do about it. So I would just call it a preprint. So if you are really interested in the paper and want to know, some of the details, feel free to reach out. I will send you a preprint or a preprint, as I will name it. So the goal of building Leo is really about to build a embodied generalist agent that is able to not only act, but also interact with humans to accomplish some perception, grounding, reasoning, and planning tasks. So to really make this happen, we would like to introduce this agent into a 3D world. And a 3D world is not just a very static world, but a variety of work ranging from like the single object and limited scene like a room, and to a scene scale like a house scale kind of thing, or even some specific working place or workplace like this robotic arm is doing right now. So to really make it happen, we may start off with some hypotheses like, how can we really design such agents to be able to accomplish such a wider range of tasks in a 3D world environment? We may start off with some large language model, because somebody has already suggested a large language model itself is very capable of doing such thing. So we can simply just prompt a large language model with anything you like GPT-4, GPT-3, or even Cloud, something like that, by just sending some system message instruction to them. And sometimes the large language model is able to produce some really nice responses, including the plans, even some interactions. But there are some huge issues, because the large language models never actually know what is happening in the world that it's situated in. So without such thing awareness, it's very likely that such language model will suffer from severe, ambiguous responses and even hallucinations. So some previous work has already suggested that prompting large language model, this large language model will definitely be able to give you some nice looking kind of plans, but many of them are not that executable in the real world or in the actual world, because the large language model has no idea of what is going on in the scene. So many of their plans are not grounded, or even talking about something that completely never exists in that scene. So to really make a remedy to this case, we may have to introduce some situation awareness or scene awareness into this model. A really straightforward idea would be converting everything like the scene into a text So we can still leverage the really nice textual interface offered by these powerful large language models. And with the help of scene captions, the large language model definitely can take a sip on what is going on with the scene. But there could be another issue too, because the thing we're dealing with right now is not just about a really limited kind of workspace. It could be a scene scale or even a very large scale kind of room layout. And in case of that, the text will be tedious because you have to describe every single details of the scene. And sometimes this can be even intractable because something we call this, because there is a really seminal concept or argument in computer vision research is called semantic gap. So you can never exhaust the details offered by the images using text. And when it comes to scene level or 3D scene level, that becomes truer. And I believe some of the recent research have been trying to do so by converting the scene from a first-person perspective into some captions. That should work, but I doubt whether this work can scale to more complicated thing. For example, like the picture here is definitely not that complicated. It's just a tabletop with just less than 3 objects. So when it comes to some real world scene with hundreds or even thousands of objects, that's definitely not doable. So I guess we may have to turn to the hard way of tackling such problem by just plumbing a 3D encoder to a large language model. I know they're going to be a huge issue when you're trying to connect a brand new modality to a large language model, but this is the way we choose to go. And by plumbing a 3D encoder to a large language model, the large language model, when it was turned pretty well, you should be able to not only produce plan by kind of leveraging its pre-trained capability, but also make sure these plans or responses are fully grounded to the 3D thing or the current situation. And with that in mind, we will be able to build a state-aware agent or scene-aware agent capacity of perceiving 3D scene, and you're performing a variety of tasks. So to really connect these large language models to a 3D world, there could be a lot of things we can do. So first of all, we can try to create a 2D branch where an egocentric view or images can be projected into some embedding that will be lately aligned to large language models. But we can also make it a little bit crazier by even connecting to a 3D branch where they will offer every single 360 view of the whole scene. And we all know that a scene is composed by point cloud or meshes, which is not that straightforward to be processed by a large language model. So we tokenize them into objects. And for each object, we will provide the model with not only their point cloud features, but also their coordinates and bounding box size or something like that. And we also perform some kind of something we call spatial attention to make sure the large language model can understand both the characteristic of each object, but also the relations among them, like spatial relations or many more other relations as well. So that really gives us the whole architecture or the design choices when building Leo. So Leo is a large language model, which is basically a Vicuña pretrained model, which specifically a Vicuña 7 billion model. And this model not only attached to a variety of prompts, but also attached to 2 encoders represent the scene. Well, one of them is a 2D encoder about an egocentric image, and another is a 3D encoder, as we mentioned before, receive tokenized object-centric 3D input. And the model is prompt to output a few tokens. And these tokens will be then decoded tokenized into both textual and actual responses in unified vocabulary space. And that really makes it easier for us to unify the task. So we'll be able to unify everything into a sequence-to-sequence problem and to train the model in a very efficient way using the autoregressive objective. But compared to previous work, we not only tune the encoder to make sure the alignment happens, we also tune the large language model a bit to make sure they can adapt to these brand new modality of 3D scene by using the parameter efficient training of LoRa. And Leo is definitely be capable of doing a variety of things, including captioning, reasoning, dialogue, planning, navigation, and manipulation. So why don't we just take a look at what Leo can do? So Leo, first of all, is able to do some really simple kind of captioning or reasoning task in a dialogue kind of fashion. So the goal of this task is really about making sure Leo can first understand the object and the relation in the scene and answer some really sometimes tedious questions by the humans. So the human can ask questions about a certain object, their characteristic, and most importantly, their relations to other objects, which we see could be a crucial part of 3D scene understanding and what 3D scene understanding could bring to the generalist agent. And some of the reasoning tasks, which is very interesting in 3D scenes, that it's not only about a 3D world, it's also about a situated agent. For example, the right arrow here really indicate a situation. And to answer this certain question, the agent has to understand the situation and answer the question according to that situation. So everything is relative. It's not just about a passive third-person view. And for the planning and dialogue kind of capability of Leo, it's more about the capability of Leo of understanding and track a long dialogue and making sure that every single message, is delivered between the human and the robot agent are fully grounded with the scene. So everything should be about the object, relations, and everything. And for the planning perspective, again, it's more about Leo to provide some really nice advice to the human, and this advice should be able to be executed in the real world. So all the plan has to be fully grounded, which means that the plan should just include the objects and also about how the layout of the room is. You can just make the thing up here, and our goal here is to make sure that the language model never hallucinate. And finally, we'll be able to also perform some really challenging manipulation tasks, like this really nice little task from clipboard. And so here's the thing: the OBA is actually control the any factor directly. So Leo is able to control the any factor, not just code the robot to do a certain task. So this is quite impressive. And as you can see, the robot is struggling, but it's getting there. And more than just that, our agent is actually doing exceptionally well on scene tasks compared to the baseline. And for tasks like this, it also showcased that Leo is able to understand some open vocabulary concept like these objects. These objects are definitely not within a certain number of categories that is trained on. And for navigation, our agent is also able to produce some low-level model control, including turning left, turning right, moving forward, and ultimately finding some object in a really large scene. All right. I wish you guys have a really nice watching for that video. Okay, so to really understand what makes a Leo so amazing, we may have to step back a little bit to look at the data we train Leo on. So we actually proudly curate two set of data sets that really make this thing happen. The first set of data set is called Leo Align, where the data set basically just includes a massive amount of 3D scene and text paired data. So the Leo will be able to align the 3D scene or the 3D scene encoder to the pretrained large language model. And another set is called Leo Instruct, where we basically adopt the idea or the concept of instructive tuning, where we collect a variety of tasks, including captioning, QA, dialogue, planning, navigation, and manipulation, and also curate some really nice instruction to make sure the Leo will be able to, after alignment, will be able to understand this instruction and perform these tasks in the real world. And through collecting this data set, we also cover a wide range of 3D scenes. So that can really range from a single object like Objectverse to ScanNet, VR Scan, and massive scene like Matterport, and even some domain-specific robotic workplace like clipboard scene. And collecting such data is non-trivial because there's really, compared to 2D, there really isn't that many data out there, pairing the 3D scene with some text. But we can kind of leverage some existing technique from 2D data collection to help out with it. So in the 2D vision language model learning, we cannot just provide a large language model with some sort of bounding boxes or scene graph. So the model will be able to understand the spatial and more sophisticated relations among those objects and their own characteristics. And with some really nice little tasks, we'll be able to generate some high quality data that not only grounded to the actual relations and the characteristics of the object, but also offer some really meaningful and diverse kind of description or even task description of this data. So such idea can be seamlessly generalized to 3D as well, as long as we have 3D bounding boxes and 3D scene graph. But no doubt that 3D is more complicated than 2D because we have an actual axis or dimension after all. So we also propose a technique called object-centric chain of thought. And that really elicits the model to produce high quality data compared to some really simple prompting technique. And here's some examples on how we prompt the ChatGPT using OCOT and some data we produce, including dialogue, captions, QA, planning, and scene caption. And that really served as a backbone of training Leo. So in today's talk, I really tend to not show some quantitative result because people seem to not care about that these days. But anyway, Leo is able to perform pretty well on a wide range of 3D vision language tasks and also deliver comparable performances on some really challenging body AI tasks as well, including manipulation and navigation. And Leo is definitely quite related to some of the recent research coming out around the world in our international community. For example, the PAMI and RT2 from Google Brain Robotics. I guess we definitely have something similar with them in terms of the task we're going to be able to accomplish and the model architecture. But we'd actually like to highlight a few differences. So first of all is that our Leo is able to perform both the perception and body control tasks by emitting the low-level model command directly. This is similar to RT2. But we can also understand a 3D scene, in the scene level, not just an egocentric video where both PAMI and RT2 is receiving. So we believe that the 3D scene is kind of like a crucial part to really power the large language model and large scale agent to actually, to ultimately serve our goal in the physical world. Okay, so that pretty much wraps out our first stage of today's talk. And now I will move to the second part, which is kind of like we step back to the digital work again and build up an agent that can perform a variety of tasks in this digital domain, which is Minecraft. So that is just about our recent series of research under the code name Craft Jarus. And as the name suggested, our ultimate goal is really building an agent that can, it's like a co-pilot when we're playing games. But it's definitely beyond our ambitious goal is definitely beyond a gameplay co-pilot. So you guys could just stay tuned on what's coming next. But today's talk, I will just focus on Minecraft a bit. So doing Minecraft is very intuitive and straightforward, and because it perfectly aligns with our aforementioned goal. Because Minecraft is definitely an open world with open-ended objectives, and it is definitely massively multitask. And to really train an agent in Minecraft, you have to leverage web-scale knowledge, and that really just suggests a clear paradigm shift from the previous embodied AI world. But an open world on Minecraft also offers a variety of challenges. So first of all, the challenge to really plan a task in open world is quite complicated because as the graphic on the left suggested, a really simple task like mining a diamond, or maybe not as simple, definitely involve a really complex task dependency graph. And a canonical planner like Street Planner, I'm not sure whether you can still adapt to these really complicated things in an open world domain. And also, what is more important is that planning an open world has to be situated. Maybe the word situated is a little bit abstract. So here's an example. Let's imagine that the Steve in the middle of the Steve agent in the middle of the Minecraft universe is trying to build a bed. So to build a bed, you may have to tailor some cloths first and to collect some ingredients. To collect some ingredients, there are a few options. You may try to come back with some spider for their spider silk. You can also try to find a ship and just to share for the wood. And it's also really pretty nice to find a little town and trade if the town needs. But the problem is that to go through which path, that really depends on the current situation. For example, in the current location of Steve, it might be better off to simply come back with Spider rather than going through a long way to find a ship or find a village. So that means the planner here has to be situated. The planner has to receive how to understand what is going on around it and make the right plan instead of just produce a plan purely based on its pretrained knowledge without seeing anything. So many of the previous research in this field have been doing exactly that because they just never send more modalities like visual, 3D or anything to the large language model. They just send the prompt, which includes the text only, to the large language model. So these models may work pretty well in a closed world setting, but I doubt their performances in a more open world kind of setting. So that kind of motivates our design of this agent, which is actually quite complicated. I know this. So I will break down it piece by piece in the following slide. So everything will start with a really nice little planner. And as the previous work, we choose to use a large language model because they're amortized, they're powerful, and they have definitely a lot of knowledge about some of the domain we selected, specifically Minecraft here. And what is different here, we tend to allow this model to produce this plan in the form of code rather than step-by-step plan, because we found it easier to parse into low-level actions to be executed by the controller. But the only issue here is that such a simple planning scheme usually won't work due to a lot of reasons. But the most obvious one is that there are going to be a lot of errors within the plan. So we have to propose several techniques to really resolve this issue of initial plans containing a lot of errors. The first set of techniques we're proposing is something called self-correction. So that includes two parts. So first off, the agent will be able to double check its own plan before sending it to the low-level controller. And that really helps a lot. And the second safeguard is that when the environment, sending some feedback like, okay, something is going off, and so the agent will be able to, leverage those feedback and maybe triple check its original plan again, and then provide a remedy on that. So here's an example. So when our agent is prompt with a task like obtain a diamond, with the help of this powerful pretrained language model, it might be able to produce a really nice looking plan. But if you look into the details, many of the plans are not that correct, especially when it comes to quantities, like the number of sticks, the number of wooden blocks we have to collect. So we kind of just ask the model to self-check a little bit, which basically serves as a double check. So as you can see, the model is able to identify some errors and to just provide a fix. And by simply using these self-corrections, we will be able to obtain a much better plan already for such a base language model. So after executing the plan for a while, the agent might encounter some of the unexpected issue because this is an open world anyway. So in this certain example, when this agent is working so hard, mining some diamonds or maybe some other thing in the underground, suddenly its iron pickaxe is broken, and there's nothing the agent can do because without proper tools, it is impossible to mine a diamond. But with the feedback and our proposed self-explanation, the agent or the large language model is able to reason about what just felt here and what the agent should do to make a remedy. In this specific case, the agent realized that it has to craft an actual iron pickaxe, and that will need some ingredients as well. So that will result in a refined plan, which serves as a remedy. And this whole process is kind of iterative, and we can going through the loop and returning over and over again until we reach the ultimate goal of obtaining a diamond. And there's another set of technique we propose here, which is called embodied RAG, or retrieval augmented generation. The whole idea is really about augmenting the existing planner, which is a large language model, with a memory. And this memory will kind of just provide enough knowledge the agent collected itself during training. So what is interesting here is that we really start off with a set of tasks, and we will ask the agent to pick a few tasks from the task pool using a technique called self-instruct. So with this type of self-instruct, the agent will be able to select a few tasks, explore the word, and store everything, including observations, plans, thoughts, feedbacks, and just all the embodied experiences into the memory. And after that, we will be able to obtain a really nice multimodal memory, and the memory is still growing. But with the help of this memory, something really nice can be done. So when a new task is coming, the agent will be able to generate a few queries that you would like to know, to really help out with the task through this kind of backward reasoning. So in this specific case of building a chanting table, the agent can think in the backward kind of fashion and to figure out if there's any specific knowledge you would like to know and would like to retrieve from the multimodal memory. And in this specific case, it becomes the diamond, the ladder, the paper, and the iron pickaxe. So these are the knowledge the agent would like to have from the retrieve from the memory. And as I just mentioned, the memory itself is kind of multimodal. So we also have to provide a multimodal query as well, which is as simple as the current observation. So by combining these two as a multimodal query, the agent will be retrieve not only the correct knowledge, but also the situation knowledge that correspond to a current specific situation. And with the help of that, our planning will be able to get much better. So here are some results. As you can see, as the song is getting more and more challenging, the advantages brought by these multimodal memory retrieval has become more significant as well. So that really suggests that to tackling a more challenging task, the memory mechanism or retrieval augmented generation or embodied RAG, as we suggested, will be very helpful. And the last piece of our agent is the low-level controller. So this part is actually not that complicated because we simply just trying to reuse some of the previous knowledge from the reinforcement learning, imitation learning community by building a really nice behavior cloning agent here. So the main idea here we found in the open world setting is really about representation learning. So representation learning in a open world setting is really crucial for the success of such a agent. So we not only propose some kind of goal-sensitive backbone, trying to fill the instruction and observation together, we also propose a set of auxiliary tasks, including predicting how many steps is still out there to reach a certain goal. And we found these two really help out with the representation and also the agent performances. And we can also combining this idea and with some pre-training as well. For example, this work from University of Toronto has suggested that by combining two pre-trained models, one is a mind clip and another called VPT, you'll be able to obtain a really nice agent that can receive text instruction and perform some shortened tasks. And we found it very helpful in building our agents as well. And here's an overview of what the current Craft Jarus agent can do, which we call it Jarus 1. And as you can see, the agent is able to robustly accomplish many of these items and ingredients in the upper world. And you can even start to collect some items that really prepares the agent for entering the underworld, which is definitely the next kind of territory we'd like to chatter maybe in the coming months. And there are also some really nice follow-up research projects built upon the Craft Jarus. Since we already came out with the project maybe 1 year ago, a lot of things are going on in the rest of the community. So that includes Voyager. This is a really famous research from NVIDIA. And we really share many of our idea on doing this interactive planning, including self-check, self-explanation, and they also have a memory similar to us. But what is different is that in their memory, they only store skills or everything they have learned before. But in our case, we store everything, like the embodied experiences, including thoughts, plans, feedback. So that really makes our memory architecture more intuitive and more similar, to an actual agent that can be deployed in the real world. And we also have Ghost in the Minecraft coming out from Shanghai Spatial Intelligence Laboratory. And this is a really nice model that leverages a powerful planner to produce a variety of tasks in the open world Minecraft universe. And we also have Plan for NC from BAAI. And what is different from this research is that this research really, consolidate the large language model knowledge into an explicit skill graph, and which makes the planning process more explainable. So that pretty much wrap up the introductory part of today's talk. And with a lot of things coming out in the past few months, and also we already doing some research around this direction, I guess we need to talk about what's gonna do next. So I guess everybody knows that unification is a key issue in today's AI because we already have some unified text model, which is dominating almost everywhere. And also unified multimodal models is roaring on all different fronts. So the next thing we're gonna chatter here is definitely about building a unified agent. I know there are already some preliminary trials into this grand challenge, but a lot of things still can do. For example, how to properly define what is a unified agent today. I know there seems to be no consensus in the community right now, but I guess we can all agree on a few points, right? So the first thing is that the agent has to be massive, both in terms of the knowledge or the data it's trained on, and also the architecture itself, at least 10 billion, right? And also the agent has to be multitasking, and that's what we call it a generalist agent. And the agent should be able to understand some multimodal input as well, but not necessarily, because some guys are maybe arguing that, okay, language agent is sufficient. Maybe it should work pretty fine in some certain domain, but in another domain, a multimodal understanding might be quite useful. So here really give us this definition. I am arguing. So I guess a unified agent is really a language piloted large-scale agent that can fulfill arbitrary goal from multimodal input in an embodied environment. I know this definition might sound a little bit, like a word salad because we don't really provide some specific details. So here it comes. I do think that on the road to unify agent, there are a few other stuff we have to tackle. So first of all is few shot learning. We already observed some really amazing few shot, especially in context learning, in unified text and multimodal models. And how about we make sure the same thing happens to the agent? Because our human is able to, even our human infants is able to master a variety of skills with just a few demonstrations. So we do believe that few shot in context learning should happen in agent as well. And also more modalities. We've been working on that pretty hard to really attaching more modality to the agent architecture. But that's definitely not the end of the road. And also beyond zero shot, we all know that zero shot agent like the jarus one we built is pretty nice, but to really empower this model, this agent with much more powerful capabilities, fine tuning or even training from scratch is definitely needed. But that will raise a whole bunch of issues, including flexibilities and catastrophic forgetting. And last but not least, there are some really unique issues with building agents as well. For example, we definitely need better learning algorithms for memory and for situation awareness. These are the things that multimodal models or text model, maybe their model they don't care about this at all. But for agents, these are very crucial to the success. And also the ability of learning from interaction, including interaction between humans and agent and among agents themselves. All right, I guess that pretty much wrap up today's talk. So before I log off, I would like to shout out again to my amazing collaborators from Big AI, Beijing and Tsinghua University, and UCLA. And without their hard working, many of the projects won't be possible. And thank you all for listening. I'm happy to take any questions.